This right over here is the graph of x plus y is equal to 1. And let's say that the region that's below this graph, but still in the first quadrant, that this is the base of a three-dimensional figure. So this region right over here is the base of a three-dimensional figure. And what we know about this three-dimensional figure is if we were to take cross sections that are perpendicular to the x-axis, so cross sections, I guess we could say, that are parallel to the y-axis. So let's say we were to take a cross section like that. We know that this will be a semicircle. So if we take a slightly different view of the same three-dimensional figure, we would see something like this. I've kind of laid the coordinate plane down flat, and I'm looking at it from above. So this cross section, if we're looking at it at an angle, and if the figure were transparent, it would be this cross section right over here. It would be that cross section right over here, which is a semicircle. If you were to take this cross section right over here along the y-axis, that would be this cross section, this larger semicircle. So given what I've just told you, I encourage you to pause the video and see if you can figure out the volume of this thing that I could shade it in a little bit. The volume of this thing that I've just drawn, this three-dimensional figure that we are attempting to visualize. So I'm assuming you've had a go at it. And one way to think about it is, well, let's just think about each of these. Let's split up the figure into a bunch of disks. If you figure out the volume of each of those disks, and sum them up, then that would be a pretty good approximation for the volume of the whole thing. And then if you took the limit as you get an infinite number of disks that are infinitely thin, then you're going to get the exact volume. So let's just take the approximating case first. So let's say that right over here at x, what is going to be the diameter? What is going to be the diameter of the disk at x? Well, to think about that, we just have to re-express x plus y is equal to 1. That's the same thing as saying that the function that f of x, or y is equal to f of x, is equal to 1 minus x. And so the diameter of this circle right over here, so let me make it clear, the diameter of this circle is going to be this height. It's going to be the difference between 1 minus x and the x-axis, or between 1 minus x and x equals 0. And so this is just going to be, as a function of x, the diameter is going to be 1 minus x. Now, if you want to find the surface area for a circle, or if we want to find the area, I guess you could say, of a circle, we know that area is pi r squared. Now, for our semicircle, you're going to divide by 2. So what's the radius going to be? So let me zoom in a little bit. So what is the radius of one of these semicircles going to be? So the radius, I could draw it like this. My best attempt to draw one of these things. So it's going to look something like this. I'm trying to draw it at an angle. So the radius, what's going to be half the diameter? The diameter is 1 minus x. The radius is going to be 1 minus x over 2. Right? That distance is 1 minus x over 2. That distance is 1 minus x over 2. That distance is 1 minus x over 2. So that is 1 minus x over 2 is equal to the radius. And so what would be the area of this side right over here? Well, if it was a full circle, it would be pi r squared, but it's a semicircle, so it's pi r squared over 2. So let me write this. So the area is equal to pi r squared over 2, because it's a semicircle. So in terms of x, I guess I could say our area as a function of x right over there. Let me write it that way. Our area as a function of x is going to be pi over 2. Let me just write that. It's going to be pi over 2 times 1 minus x over 2 squared. So it's 1 minus x over 2 squared. And so if I wanted the volume of just this disk right over here, I then multiply that area times the depth. I just multiply the area times this depth here. And we could call that dx, or we could call that delta x. So we could call the depth there delta x. Delta x. Now, that's the, actually let me be clear. That's the area, the volume of one of those shells is going to be equal to, and I'll just write this in one color, it's going to be pi over 2 times 1 minus x over 2 squared times the depth, the area times the depth. So this is volume of one of these half disks. Half disks. So the volume of the whole thing we can approximate as the sum of these, or we could take the limit as our delta x's get much smaller, and we have an infinite number of these things, which is essentially, if we're taking that limit, we're going to take the definite integral. So we could take the definite integral, so the volume that we care about, the volume of this figure, is going to be equal to the definite integral from x equals 0 to x equals 1, that's where we intersect the x-axis, x equals 0 to x equals 1, of, we're integrating an infinite number of these things that are infinitely, I guess, thin. So it's going to be, let me write it, it's going to be pi over 2 times, I'll just write it, what's 1 minus x squared? Let me just expand it out for fun right over here. So that's going to be, that's the same thing as x minus 1 squared. So it's going to be x squared minus 2x plus 1. And then 2 squared is 4 over 4. And instead of delta x, I'm going to write dx now. I'm going to write dx because I'm taking the limit as these become infinitely small, and I have an infinite, and I'm summing an infinite number of them. So the volume is just going to be, we just have to evaluate this definite integral. And if you feel so inspired, if you feel inspired at the moment, feel free to pause and try to solve and try to evaluate this definite integral. So let's just take some of these constants out. So let's take pi over 8 out. So our volume is going to be equal to pi over 8 times the definite integral from 0 to 1 of x squared minus 2x plus 1 dx, which is equal to pi over 8. And so the antiderivative of this is x to the third over 3 minus x squared plus x. And we're going to evaluate that at 0 and 1. 0 and 1. And so this is going to be equal to pi over 8. When you evaluate it at 1, you get 1/3 minus 1 plus 1. So it's going to be 1/3. And when you evaluate at 0, you're going to get 0 minus 0 plus 0. So it's going to be minus 0. So it's just pi over 8 times 1/3, which is equal to pi over 24. And we are done.